Xiong from Huangzhou Agricultural University, China, and Georgiy Bobashev from RTI International. And they will be talking about testing hypotheses in agent-based models.
All right. Thank you very much. So how do I do it? So I need to probably share the screen.
Yeah, you are a co-host.
Right. So, okay.
Should be at the bottom of.
Right. Okay. So can you see my screen now? All right.
It's coming up.
Just,
yeah. Okay. We can see
it. Get the slideshow. Oops. Oh, sorry.
We should probably give you a little bit of extra time because we sort of bleeded
off
the schedule.
Thanks.
All right, Georgiy.
All right. Yeah, my name is Georgiy Bobashev, and this work is done in collaboration with Professor Xiong at Microagricultural Institute in China. So we'll be talking about hypothesis testing in agent-based models. And I just wanted to say right away that I'm wearing multiple hats. So my background is in physics, in engineering, in statistics, in agent-based modeling, and social science, so epidemiology. So this perspective is more given from statistical point of view. So I'm trying to be more a statistical technical from this perspective. And that perspective tells me that, well, agent-based models are not any special types of models. So I'm viewing the whole set of simulation tools as a continuum, and so or hierarchy in a sense. And so we start with statistical models, Markov model, system dynamics. So these models based on the major concept of IIDs. So we don't care about a single individual, so we can work with a mean field approximation. So we collapse everything and work with mean fields. But then when we really want to consider a lot of heterogeneity, we get to the micro simulation route. And so agent-based models are just representation of micro simulations where we also have interactions between agents. And so the more complex questions we want to answer, the more probably complex of the model we would like to include. And I think one of the biggest challenges here have been kind of like dualism of Occam Razor and system science approach. So on one hand, we just really want to have a very simple model. And on the other hand, system science will tell us that we really want to have, like multiple components to consider multiple interactions. So I think Einstein, well, he wrote a paragraph about that, and which is usually quoted as the model should be as simple as possible, but not simpler. And so, well, that doesn't help much. But what I was thinking about from statistical point of view, that, well, the statistics we have variable selection algorithms. So we can think of stepwise algorithm, we can think of lassos, we can think of random forests, whatnot. So the question is, can we develop similar algorithms for agent-based models to say, well, if we have a complex system, we have the whole bunch of different rules and components that we want to include, where should we stop? And that's, again, a big question, so I don't have answer to that yet, but we say, okay, well, when we use in statistics variable selection algorithms, we run some kind of tests all the time. And so these tests, the way you look at it, they could always be viewed as some kind of hypothesis test. So essentially, is there a difference between model with additional parameter or not? Or should this parameter or this variable be included or not? So that's a little bit simpler test. I mean, it's a simpler task, but still quite complex. And I will talk about several specific technical questions that arise in this context. So first of all, the area where I'm working is not much theoretical agent-based models, but they have to be practical. So we work a lot with data, and we need to have models to be calibrated, validated. So the first question is like, okay, is the current model output close enough? So if it's close enough, maybe we should stop. We should not add more components. Or maybe we should. Again, this is one of the questions. So if we have models set up and the only thing we do is we adjust the parameter value, that's our standard calibration. If we try different structures, this is becomes more inverse engineering. And so when we want to answer these technical questions, we really want to formulate some kind of like formal tests, and so that we can make a decision to say, okay, to say, yes, this model is close to the data or not. So most of the time we do that with our two eyes, and we say like, oh, look, this curve goes this way, and our model is going, when I was a student in biomathematics, my mentor, Steve Elner, said like, well, what statisticians don't understand often is that in biology and also in economics, if you get the sign right, you already have a success. So like, especially in economics, you guys understand it more. Okay, if you know whether the stock market will go up or go down, so which side you play, right? So what we're thinking from this perspective is that if we have a structure, like how we define structure, it could be logical structure, or it could be an equation, but in some ways there is a parameter in there. And so what we're trying to do is to say, okay, if there is a parameter, often there is a situation when if you set that parameter to 0, that structure will disappear. And so this way, we just really want to develop some tests that, okay, if parameter is close to 0, and I will say in a minute why saying 0 is bad. So if that parameter is very small, okay, we should ignore that structure. So I'll also give a few theoretical and practical illustration down the road. But then when we start talking about like, oh, okay, let's do some hypothesis testing, and then suddenly we realize like, well, they are quite a number of ways to do hypothesis testing. So at least statistics offering us two approaches, frequentist approach and Bayesian approach. And they differ in principle of philosophy. And people often confuse them and just say, oh, okay, just have a general notion of hypothesis testing. Right, when in frequentist approach, we say, okay, given the structure, given the null hypothesis, what is the probability of observing that data or observing this pattern? And if we see that given the structure, the probability of observing the data is small, then we reject the hypothesis, right? Bayesian approach is totally the opposite. We'll say, okay, what is the probability of null hypothesis given the data? And this is where I think we have much more interesting things going on with agent-based models, because that kind of like alludes more towards structure, to say like, we just don't want to reject a certain structure, say like, no, this structure is wrong, this don't be binary. We'll say like, well, this structure might not be as good as the other. so these are some interesting things, like philosophical and technical. So to me, Bayesian approach is more natural way applicable to agent-based models, and frequentist is more common because that's how most people, most statisticians are being trained. But another thing I wanted to mention here is that Bayesian approach considers a distribution of parameters, that there is no such a thing as a single parameter. It's not like, this, you pull a slider and it's the value of parameter is 3. No, you say, okay, there is a distribution of that parameter, and that's what we usually deal with when we build models for practical purposes. So I will now say a few words about differences and similarities in hypothesis testing in statistics and simulated models. So one thing I just really want to emphasize, that we should not have a hypothesis, a traditional frequentist hypothesis, in a sense that parameter is 0 versus parameter is not 0. And the reason is that if we follow traditional frequentist approach here, and this is where things get wrong, these approaches are based on the notion and definition of standard errors. And standard errors have the number of observations in the denominator. And so if we have a simulation model, we can generate as many simulations as we can. We can have, like, millions, billions simulations theoretically. And so our denominator could be very big, so that any effect that we want to test, any effect will become significant. So how we deal with that? Of course, in clinical research, they have dealt with that all the time, and there is this whole concept of minimal effect size, minimal meaningful effect size. So rather than saying whether these two parameters differ or whether our parameter is not different from 0, they say, can we actually prove that these parameters are indistinguishable statistically? And so what they do often is, when you have a generic drug and you really want to statistically test that generic drug is not statistically different from the brand drug. So you really need to show, to define that interval. And that's the solution for large computational numbers. So if you generate a large number of simulations, you can potentially prove that, well, statistically there is no difference. So when we deal with statistical testing, so we really need to also consider sources of uncertainty. And so specifically, I'll be talking about structural uncertainty or robustness. So there are a number of sources of uncertainty with input data. There is, of course, deep uncertainty, all kinds of stochastic internal uncertainty in simulators. But for inverse generating models, the uncertainty in, like, structural uncertainty is important, but we shouldn't ignore other types of uncertainties. All right, so I'll give a couple examples again, just everybody's using using Schelling segregation models. So a couple of examples how frequentist approach could be used to testing. So, for example, somebody tells me, hey, we just ran, like we found some simulations by Schelling segregation, so the paper or results, and we see that percent similar is 75.5. So can you tell me which parameter is, well, percent similar wanted is the most likely to generate that value? And that becomes a calibration task. So we really want to find the parameter space to say, okay, which parameter is more likely to produce the desired result. The problem, of course, is that there is any value between 25% and 37.5%, because the likelihood for this model is pretty flat, because essentially, even though the slider here, and this is what becomes misleading, the slider is continuous. You can say, okay, 30%, 31, 32, 33. But essentially, when you're thinking of the neighborhood, you only have 8 neighbors. And so you can have, you know, 1 neighbor similar, 2 neighbors similar, 3, 4. So it's everything is going in 125% increment. So we get like a stepwise likelihood. So that's usually big difference from traditional hypothesis testing. So there could be another example of hypothesis testing. So again, somebody says, okay, percent similar is 75.5. Could this percent be produced with parameter value of 40%? And so then we can run the model many times, develop the simulation, say like, well, the answer is very unlikely. So I ran it 2,000 times, and only one time it got close to 75.5. So yeah, the probability is very small. So we can extend that to situations when it's not just a single number is given, like 75.5, but multiple numbers, and then we can just deal with means. So one thing I wanted to mention here is that this frequentist approach could be very useful when deciding how many simulations to run. Again, I just wanted to reiterate that if we say what's the probability of getting a result of 75.5 with parameter 30, the answer is 0, because when you run it many times, you get the whole distribution, and so you never get that exact number 75.47. You get 75.478113, whatever. So you get the whole distribution. So the chance that you will hit a single number is is very small. So, but what we can do is we can say, if we give the range and we say, okay, we just really want to know how many simulations to run to get our mean within that range, so that with 95% confidence, you know, our mean will be found in that range. And so for Xiong segregation model, again, we just give the range plus minus 0.1, the answer is 420 simulations, which is a useful approach. All right, so let me quickly show how it was done in a practical, like big model that we developed. So it's a model of heroin drug market, and so we have a complex, it's just a diagram of daily activities of heroin users. And so it's run with half-a-minute time steps. So it just describes things in very minor detail, how transaction interactions are done with dealers. But we want to measure market performance over the course of a couple of years. So we really want to have a much bigger time step. So we really want to collapse part of this component. So when individuals walking around the market makes the deals, what we really want to say, okay, if a drug user really wants to get a drug, what's the probability that the person will get the drug and not get arrested? If we use a distributional approach, so we just want to use some form of emulator, like Gaussian emulating process, we will not get the right results. So we really need to build some statistical model. And in this case, we build a regression model based on a number of internal factors to produce that probability. And so what I wanted to show here, so we have a full model, which is a trajectory in black. So this is the average tolerance the need for drugs a person has in our population. So this is how tolerance builds over time. And so if we collapse the model and rather than half minute time step, use 2 hours time step, this is the model that we get, and we see that this model is not any close to this black original model. If we use the regression model, like much more complex model, it's still a simulator. It's still collapsing that moving around. So we can get a much closer results, and we came up with these hypothesis testing. So it's as you can see, these are the formal p-values for similarity between these trajectories, and you can see that, okay, here the p-values are close to 1, so well, these trajectories are not any close. But here we say, okay, at the beginning these trajectories are not very close, but eventually they become very close. And so we did that for a number of other variables in the models, and so essentially just showing that, building those emulators on some components of complex models will make those models much better. So the next example is Bayesian approach, and Bayesian approach is a little bit different. So again, the same, we need to build an alternative null and alternative hypothesis. But then we need to define the criterion function, likelihood ideally, to say how can we estimate the parameters, assume prior distribution, and then by running models many times, we need to estimate the posterior distribution, and looking at posterior, check the hypothesis. So okay, I will just skip lots of well, theoretical part. Just I described that. I just go directly to an example that Professor Xiong was doing of his agricultural model. So it's a very complex agricultural system where he was modeling how farmers in China adopt new crops. And so the question is like, if the village used to farm certain crops, but then it turns out that the needs of market have changed and the government really wants individuals to adapt fairly quickly, and it is a multi-component, very complex model. So we really need to explore the factors and explore different strategies that the government could use to make sure to make that adaptation fast and least painful. So one of the key parameters there that we really want to consider is experience of relatives and externality effect. So experience of relatives means that household probability to adopt a new crop depends on proportion of satisfied adopting relatives. So individuals have their network, and so they want to look at their network, and depending on so it's a continuous function, and we would like to model it with some logistic regression, but we don't know these parameters and don't have data. The only way to estimate these parameters, specifically this parameter gamma, is to run models many times and estimate it through calibration process. Externality effect is the next level, is to say, okay, if the family does decide not to adopt based on experience of relatives, maybe it could adopt based on the number of households that are neighboring households that might not necessarily be family or relatives, based on that, if they decided not to adopt based on relatives. So we want now to test whether we would like to keep these components in the model or not. So we say, okay, we just really need to get some ranges to say, okay, these are the ranges of parameters being small. So let's put 0.005. If those parameters turn out to be that small, then we will ignore that structure. And so what we did, we need to give up, design some kind of like measure of likelihood. But for most models, it's very difficult to develop or define likelihood because we don't have a structure. So we will use not pure Bayesian approach, but more approximate Bayesian computation approach, where rather than looking at the likelihood, we would develop posterior by drawing from the prior distribution, and for each run, check whether we are within our desired threshold of accuracy or not. If we are within, we keep that parameter. If we are out, then we throw that parameter away. So this way, we run it many, many times, and we get posterior distribution. So we, for each of the parameters, we give the prior distributions. So they are almost flat, but like stepwise flat. And run models many, many, many times, get posterior distributions for parameter gamma and for parameter h. And so this is the final result. We see that for experience model only, we just get the value of gamma, which is far away from being small. So yes, this effect is very strong. But for externality, so when we combine effect of relatives and effect of neighborhoods, we see that effect of neighborhoods is becoming very small and could be negligible. So we might remove that structure from the model, even though like in the actual study we didn't, because digging deeper, realize that there are conditions or situations when these things become important, but that's a different story. But this is an illustration of how Bayesian approach could be used in agent-based models. So in conclusions, I just want to say that, okay, first of all, we just really need to have more discussions about why do we need to do hypothesis testing in ABM, just giving more and more examples of where hypothesis testing is needed. And the 3 or 4 examples that I tried to give today, they're just, 4 examples out of maybe, 10, 15 that I can come up with, like ideas where hypothesis testing becomes useful. But then there are interesting things that we can think, okay, so now we were testing hypothesis on specific structures, but these specific structures could be at individual level, they could be at the global level, they could be at the structural level. So, there are interesting, so there are a lot of work to be done by statisticians and collaborating with modelers. Of course, one of the biggest issue is what if we have, thousands of parameters and only 10 observations. This is what we have, for example, for opioid modeling, when we, have 10 years of data and we just look at opioid mortality. So we have like 10 observations, but our models have lots and lots of components. And of course, we can calibrate the model really well. But the question is, if we start throwing away components, when we have so many other components will take care of what was thrown away. Like here, if we have both effects, then this relative effect is 3.6. If we throw away the effect of neighbors, the effect of relatives becomes 4.1. So it will take part of variability on its own. So the question is it the right way or not? But it's like with human body, when something stops working, another part of the brain or another part of the body picks up to compensate. All right, and so again, lots of testing that we've done is within model testing, assuming that all other parameters and other structures are staying the same. So what if we start blowing everything out? Okay, let's vary everything, as we saw in the sources of variation. And yeah, so this seems to be an exciting area, and I would like to collaborate with whoever would like to collaborate on that topic. I also need to acknowledge our funding from a National Institute of Health, specifically NIDA, National Institute of Drug Abuse, and so.
Great. Thank you so much, Georgiy. Great talk. Very interesting statistical perspective on the IGSS problem. I really liked your example with the households. It reminds me of the Anasazi problem. And do you have a publication on this work? I think it would be really helpful if you could share that maybe on the Slack channel.
Yeah. So we have a couple of publications on. Okay, so yeah, I will share them. So
yeah.
So we have a couple of publications on the farmers. So it's and then we have, oh, I forgot to mention publications. This is we did with Daniel Hurd and Lee Hoffer.
Yeah, that would be great to read if you could share that. That would be very helpful. All right.
Yeah.
Great. I think we're a little over time, so I'm going to move over to the next talk. Thanks again, Georgiy. So our next talk